Greetings, salutations, all those nice things. Today we are going to look a bit more at limits and also just how to evaluate some limits using substitution. We can think of this as a U substitution if you want. And in some of these cases, it's not going to be the only way that we have to use, but it can be very useful in some circumstances. Now, take a look at this. Limit as x approaches 1 for this whole chunk-lunk of nonsense. We've got sine of ln of x to the 5 all over ln x. Now we can rewrite that a bit using a logarithm law. Take this 5 and plop it in front. So that would be my first step. So this thing is equal to the limit as x approaches 1 for sine of 5 ln x over ln x. So that's the situation. Again, this is super L'Hopitalable. Is that a word? It is now. But there's other ways we can approach this. I can let u equal all this garbage in here. I'd rather just take like sine of one straight up variable. That would be great. So I will let u equal 5 ln x. And the thing I'm going to note is that as u approaches, as x approaches 1, so as x approaches 1, u is going to be approaching 5 ln 1. And because ln 1 is 0, 5 ln 1 is also 0. So that allows me to rewrite this limit. As x approaches 1, u approaches 0. So that change has been made. Because as x approaches 1, u approaches 0, just based on this definition of u. This 5 ln x is going to get replaced with u. And then this ln x will also get replaced. Now u is equal to 5 ln x. So ln x on its own would be u over 5. Written slightly differently, without the complex fraction in it, this is 5 sine u over u. This is still, an indeterminate form situation because sine of 0 is 0. Bottom is just also straight up 0 right now. So 0 over 0, no go. We can L'Hopital this, or maybe you just straight up remember it at this point. Who knows? But if we do go with L'Hopital from here, then we're talking about derivative of the top, which is 5 cos u, and derivative of the bottom, which is 1. Which then gets us, oops, I don't want a limb there, just straight up 5 cos of 0. And that is equal to 5, since cos of 0 is equal to 1. We've seen this one a couple times already. I strongly recommend memorizing it. So the limit as the argument approaches 0 for sine of that argument over that argument is straight up 1. But here's why it happens. So it's not the only way to approach that. We could have just L'Hopital this from the beginning, but this does provide us another option. And that option is handy because sometimes it is kind of the only way we can proceed, but also we'll see how that applies graphically at some point in our lives. Let's take a look at the next example. Okay. Limit as x approaches infinity for this whole thing. We can actually get this via squeeze theorem if we want. But again, going to show you this other way to handle it. Again, I'd rather this was just sine of variable and not sine of some function of variable. So I'm going to say that u is whatever that argument is, which also means that u is 1 over e to the x. So then, as x approaches infinity, using infinity because that's what's plunked in there, u approaches, well, this would be 1 over infinity, which is 0. So rewriting this limit, this is the limit as x approaches infinity for e to the x sine of e to the negative x, which is the limit as u approaches 0. Now, e to the x is the reciprocal of u, so that's 1 over u. And sine of e to the negative x is going to be sine of u. So this is then the limit as u approaches 0 for sine u over u. And oh, we know that one. We're so familiar with it now, ever since the last page. If we want, we could L'Hopital it, because why not be certain? We then get cos u over 1. So that's cos of 0. And that's 1. But again, super recommend just memorizing this whole limit. You see sine x over x as x goes to 0, that's 1. So when we work with directional limits, we've always thought of approaching from the right and approaching from the left, which can be handy, works well when direct sub can be used. When we do have functions of functions, like in this case, a function of a function, or in this case, a function of a function, we might want to be considering what's happening in each nested layer with more of a consideration of, are we approaching from a higher value or a lower value? So this next example, we're eventually going to get to here. Here's our next page. We're not there yet, but that's what we want to evaluate. We want to figure out what e to the power of secant of x is approaching as x approaches pi over 2 from values higher than pi over 2. Or in a sense, from the right, but try not to think of it that way. Preparing for it. What does cosine of x approach as x approaches pi over 2? Well, we can consider what that giraffe looks like. I've done better cosine graphs. I've still done better cosine graphs. That looks decent. So there's your graph of cosine. And we know some values in here, but that right there, that's where x is pi over 2. And we could say that as x approaches pi over 2, cosine of x approaches 0. Cool. But we're looking at this from values greater than pi over 2. So not just approaching it at all, but specifically from values higher than pi over 2. So getting to pi over 2, but from this side. And moving that way has this directionality. We are approaching 0, yes, but not from above, from below. So we can say that as x approaches pi over 2 from values higher than pi over 2, cos of x is approaching 0, but from values less than 0. Again, because of this directional arrow, we're going from higher than pi over 2 and then moving towards it. And that causes, as we move left, that causes us to also move upward. So we're approaching it from a negative or a downward direction, going higher. So, since we also know that secant of x is 1 over cos of x, we can look at that graph as well, if you want. Which is something like this-ish. As x is approaching 0, secant of x is getting kind of undefined. It's trying to either go to positive or negative infinity, but we're going from this side of things, from greater than pi over 2, which means, whoa, I want my asymptote in a different color. Which means we're approaching from this direction, and we're following the curve then this way. And that's what's happening. We don't have to do it from the graph. We can just note it from cos x itself, but as x approaches pi over 2 from higher values, cos of x is approaching 0 from lower values. So cos of x is being negative, close to 0, but negative, which means secant of x is approaching negative infinity. And again, we see that here graphically. But a huge key here, again, is that as x approaches pi over 2 from above, u is approaching negative infinity, and that is if u is equal to secant of x. Note, there's no direction associated with approaching negative infinity. It's only possible to approach it from higher values. But this, super key in evaluating that limit on the next page. Let's take a look at it. Whoa, my goodness. Oh, it still looks so gross and scary. Oof. But we can manipulate this, because I will let u equal secant of x. And as we've noted, as u approaches, as x approaches pi over 2 from above, and using that because that's the limit assigned to us here. But as that happens, u approaches negative infinity, since we've already established secant of x would approach negative infinity. So the limit we are after then, this lim as x approaches pi over 2 from above for e to the secant of x, is equal to the limit as u approaches negative infinity for e to the u. There's a bunch of ways you could handle this. I would recommend considering the graph. So e to the u looks like this. And as u goes towards negative infinity, this thing goes pretty much to 0. You could do another round of substitution if you want. You could let v equal negative u and go from there. But this is probably your fastest way. Dare to try the next example. It's not like the most straightforward thing in the world. You will have to picture some graphs and stuff, but at least give it a try and spend a solid 5 minutes on it before resuming this video. But pause this video now. Okay. Yikes. As x goes to 0 from values above for arctan of ln of x. I could do that. No sweat. And so can you. Speaking of u equals ln x. And I want to picture what happens as x approaches 0 from values more than 0. When I do that, I'm looking at this graph of ln of x, which I know kind of looks like that. And as x heads towards 0, these values start to go super negative. And with that directionality, I can establish that as x approaches 0 from values above, u approaches negative infinity. Rewriting my limit then, arc tan of ln of x. This is equal to the limit. So as x goes to 0 from positive land, u is just straight up heading towards negative infinity. And we're taking arctan of ln x, but ln x is u. And now we need to figure out what this value is. Again, I would approach this graphically. You can picture what tan looks like. Tan of x has a couple of barrier asymptotes, but has this kind of shape. So that's a thing we know about tan. So arctan, its inverse, looks more like this. So by picturing it, I can get this value. As u goes towards negative infinity, this is what we're trending towards. So the question is, what's this lower barrier? Which is then also, what's this particular value? And that particular value, we know, just based on the graph of tan x, we know that to be negative pi over 2. And then that one is done. So this idea of approaching from higher values, from lower values, etc., that can also be used when we are determining limits from graphs. Now this says state, so you don't really have to show any work, but realistically in an AP exam stitch, this is probably showing up in multiple choice, so you're not showing any work anyways. But we've got graphs. This is the graph of g of x. This is the graph of h of x. And I know that because they're labeled as such. We're also told that f of x is using some function composition. So this is saying f of x is h of g of x. And we want to know what's happening to f of x as x approaches 1 from values below. To get that, we'd want to figure out what's happening to g of x as x approaches 1 from below, and then use that to figure out what's happening with h of x. So in our head brains there is something. We're going to note that as x approaches 1 from below, g of x, what are you doing? So here's 1 itself. We are approaching 1, not from this direction, not from the right, not from higher values of x, but this direction, from lower values of x. So we're following this particular path. That means we are approaching a y value of 1, and we're doing so by going downward to get to it. So we're approaching 1, but from above. G of x approaches 1 from above. So then, as g of x approaches 1 from above, h of g of x approaches something. So the input for h is approaching 1 from values higher than 1. So here's our 1. H is approaching values from higher. So from this side, we are moving in that way, which means that we are following this particular path. So to go leftward to 1, essentially. From the right side, we have to move left. That's the path we're following, and h is approaching, how do you say, straight up -2. So the value here is -2. We don't need to state it's approaching -2 from above. That above or below, it only concerns us if we are proceeding further with that limit. So if there is some other function based on f of x, then sure, we'd consider that we are not just approaching -2, but that we're doing it from above. Because it's just, what's our end result? What's our value? We're just stating the value. Quick, try the other one. Je dare you. Maybe I'll switch colors for it so you can see my color application. But try it. Take like 2 or 3 solid minutes right now. Pause the video and then go for it. Pause now. Welcome back. I'm going to make some considerations here. So x is approaching 1. From values higher than 1. So here's my 1. I want to approach from higher values, so I want to come in from the right. So following this, I'm going here, and g of x is approaching 3. And it's doing so by going downward. So it's doing so by taking on higher values. G of x is approaching 3, also from above. So, as g of x approaches 3 from higher values, h of g of x is doing what? So as the input for h approaches 3, well, here's 3 for h of x, and we're approaching from higher values. We're approaching from this side, moving in that way. So we are following this path. And that path, as x gets close to 3, y gets close to 0. And for that reason, that limit is equal to 0. Well, are there any questions, comments, concerns? Quick show of hands. I can't see your hands. This is a video. But I guess take a moment to relax or something, or do some midterm practice. Follow your heart. But this lesson is done. And I will see you in the future. The end. Stop recording. Help. I need an adult.